Hello. Yeah, welcome to session number 11 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this session, I'm going to talk about planar antenna designs, and I'm going to start with the simplest structure, which is a rectangular patch. I'm going to use the same substrate which I have created, which is a LTCC substrate, and I am going to use three. Okay, so let's consider these three layers of this tape, which is going to be 97 into 3, right? So 97 micron into 3 is the total height of the substrate, and the ground plane is going to be on M4, and the radiating patch would be on M7. So let's get started, and let me first explain you that there is a separate playlist in my channel which is on the antenna design, and if you want to look into the mathematics of it, so the equations I'm going to write here is based on the cavity model which I have derived in my other playlist which is on antennas, right? So if you want to uh, see that playlist, you will have more idea about antennas. So over here it's going to be just a implementation, so you won't find a lot of theory here, but I'll explain you in brief what a patch antenna is. So what a patch antenna is a rectangular ground plane, right? And on top of this rectangular ground plane there is a substrate of certain height, right? And that substrate of certain height, let's say, is this one. And let me just edit its properties. Edit formation fill. Okay, so I can see underneath this is my uh, substrate, and the substrate has a certain height. Okay, and then on top of it there is going to be a patch, right? So let me insert a patch here. So let's say this is the patch, right? And so let me just, okay. So now patch has got two dimensions here, right? So one dimension is I will address as a width. So this is the width of the patch. So let me change the, so this is the width of the patch. And then there is this length of the patch. So this I consider as the length of the patch, right? So say width of the patch and the length of the patch, right? Now why I refer to this as a length is because this is the resonant length, and if I was to draw the current and voltage waveforms across this length L, then it will look like this. So let me just take this, and let's say along this length, let me change the color of this. Okay, so along this length I am supposed to look at what the waveforms would be. So if I first look at the current, okay, so okay, so if I was to look at the current would be doing something like this. Rather, I want to make a sine wave, right? Insert shape. Okay, so let me draw this again. Okay, so this is what the current distribution would be like. Okay, so this is going to be my current distribution. Just one second. Oh, come on. Okay, let's assume this is a rough figure. I'm not good at drawing. Okay, so this is my current distribution. And let's look at the voltage distribution along the patch. So the voltage would be doing something like this. Again, some problem with the placement of points. Okay, roughly this is the best I can do at present. Okay, so this is going to be my voltage distribution here. Sorry about that. So this is my voltage distribution, this is my current distribution. Now the currents are zero at the edges because there is no way for the current to flow, right? And the voltage are maximum at the edges because it's open circuit, the voltage would be maximum, right? And somewhere near to the center you have a voltage crossing zero where the current is maximum. So in that case the impedance over there is zero, right? So I am going from, so basically in terms of impedance I'm going from 0 ohm to somewhere infinity, correct? So let's look at this. Let me write it down. Format, insert symbol. Is there infinity quickly? That's horrible. Can't find the infinity. Just 1 second. So here it's easy. Okay, so I'm going in impedance from 0 to infinity, from the center of the patch to the edge of the patch, and somewhere in between there is going to be our 50 ohm, right? So somewhere there would be 50 ohm, and the idea is, okay, so this length of the patch, of course you can understand this length is 180 degrees, so this is lambda by 2, right? So the length of the patch is lambda by 2, so let's write that. So the length of the patch is lambda by 2, right? So this is lambda by 2. So I'm going from the center to the edge. So this is lambda by 4, right? So I'm going from 0 to infinity by a line which is lambda by 4, right? And somewhere in between there is going to be 50 ohm, right? So this is where I would put my 50 ohm feed, right? So you understood how this is working. Now what the current is going to do? The current is going to set up a, a field, an Etch field, right? So an Etch field would be, let's say, concentric circles like this one. Okay, just 1 second. Okay, so the Etch field would be because of the current, and let me draw it here. It would be like a concentric circles, right? Something like this. Okay, so this is your Etch field. Okay, why I'm considering this is because you should understand that the design is just not a random magic which some of the antenna guys write some empirical equation and call that is the design equation. I don't want to do that. Okay, so what you have is this concentric rings around this length. Okay, so let me repeat that. So there is this length and then there is this concentric ring. Now, what about the H fields? Sorry, the E field. So the E field is going to be shape. Okay, so the E field is going to be something like this. Okay, going from one terminal or one end of the antenna to the other end of the antenna, The E field is because of the potential, isn't it? So the E field is because of the potential, and it will be like this. Right. So you can see the direction of E. Okay, so the direction of V is along the length, right? So let me draw the direction of E. So the direction of E is along the length. So this is direction of E. It can reverse, so it can basically oscillate like this. It will oscillate like this, right? It will go one direction, other direction, depending on what the voltage is doing. And what the voltage is doing like this, right? It is basically going negative and positive, right? So the voltage is doing this, and the electric field is doing that, correct? So now I consider electric field to be along the length L, and the magnetic field, okay, and the magnetic field is going to be along the y-axis, or along, you can say, the w-axis. If you look from the top, right, it is going to be along the w. Okay, so let me draw in 3D. So it will be oscillating like this, right? So because these concentric circles, right, these concentric circles, so it is tangential field, right? So let me show you over here. So it is a tangential field like this, right? So this is along a circle, right? This is along a circle. This is tangential. So you use the right hand thumb rule. You will see that this will be along W, right? So along W, this is going to do this. It's going to oscillate like this. This is because the current is doing this, right? If the current is doing this, then these concentric circles around this conductor are going to become smaller. Then the field will reverse direction. They will become bigger, right? So this is going to do this, right, with the current. So now this, okay, so this is E and this is H. So if you were to do E cross H, okay, that will be the direction of propagation. But now here uh, it is going to be, let's see, it's the source, right? So this will be around that direction, right? So now if E collapses into H, then the direction of propagation would be S, which will be along this direction, right? So let me make this. Okay, so that's what's going to happen. Okay, now there is a slight difference between the way you see the line and the way you see here. Okay, uh, so you think it in terms of a source, right, with which is lambda by 2, right? So this is what's going to happen. So you are going to have fields which are going to radiate out of this patch, right, in the direction which is going to be the normal to this plane, right? So it will be coming uh, off the screen, right? You can imagine like that. Okay, and then you can see that if you take these lines, then this will be looking like a paperweight, right? So on top of this patch antenna there is a paperweight, and along the W direction there is going to be your H fields, and along the L direction there is going to be your E fields. So this is how a patch antenna is going to radiate, right? Now we will plot this to see if really this is happening, and also we will plot the currents and voltages to see really are we getting this kind of a waveform, right? So this is after the simulation. That's the post processing. So I hope you understood how an antenna works. Now the next question comes is, how do you design it, right? Now the issue is this patch has a certain length L, which is supposed to be lambda by 2, right? But then if you make it lambda by 2, the patch is going to be looking bigger than lambda by 2. Why? Because there are fringing fields on these two edges, right? Two non-radiating edges, you are going to have fringing fields here. Now these fringing fields will cause the the length to go up, right? So then the effective length you should design for should be lambda 2 by 2 minus del of L, right? Where del of L accounts for the fringing. So the physical design L is smaller than lambda by 2 by del L, and the del L is decided by the fringing, and the fringing is decided by the height, right? Fringing is decided by the height. Okay, fringing is decided by substrate height, correct? So, and this fringing, okay, is decided by the substrate height. Now you want most of the field to be in the air rather than in the substrate. So what does it mean? It means that the dielectric constant should be as low as possible, and the height should be as high as possible, right? So you understand that in case of a transmission line, you want the height to be small, substrate height, because you do not want to radiate out of a transmission line. You want to transmit something, right? While in case of an antenna, you want to radiate, so it will be opposite of that. So you want the substrate to be taller or height to be more. And second thing is you want the dielectric constant to be less. So in case of a transmission line, you want dielectric constant to be more because the structures are going to be smaller, right? But if you make structures smaller, then most of your field is going to be in the substrate, and so that's what you want in case of a transmission line. And in case of an antenna, you want the opposite of that. So in case of antenna, you don't think of shrinking the size of the antenna by increasing the dielectric constant, because that's counterintuitive to what we are trying to do. We want to radiate more, so that means that the the dielectric constant should be as small as possible, right? So if you, and what that will do, that will increase the radiation efficiency. So what is the radiation efficiency? So if I put in like x power, and let's say I'm radiating y out of it, so y by x into 100 would be your radiation efficiency. And then if there is a mismatch included also at the feed, then the y by x and then the additional loss because of mismatch, that will be called system efficiency. So when we design an antenna, we don't only look at the radiation efficiencies, we also look at the system efficiency. Okay, so this is one parameter. The other parameter is going to be the gain of the antenna. Now if I consider just a source, a point source, then the radiation will be like a sphere, like a ball, right? So this is called isotropic radiation. Now if I consider a piece of a wire, then it will be like a donut, right? So this is called omnidirectional, right? Now in case of a patch, it will be two such slots, right? So one is on the left hand side, the radiating slot. So one is over here, sorry. So one is over here, which is doing the same thing as over here, right? So there are two of them, right? So they are coupled, right? So the slots are going to be coupled. Another thing is that these non-radiating slots are coupled. So when non-radiating slots are coupled, what's going to happen is this waveform is going to move, right? So this waveform is going to move. So you understand the coupling between the two non-radiating slots will cause the 0 ohm not to be at the center, but it will move it to one other side, right? So you can understand this way also. The coupling can cause something like this, right? So that means that my feed point has moved to the right, right? So what I'm trying to say is that the coupling is also important, okay, when you do the design equations. So in my design equations, I'm going to write coupling also to when I try to figure out the feed points, right? So that's the cavity model, which I discussed in my another playlist, which you can see in detail, and these equations what they mean. So I'm going to first write these equations to design a patch, write the equation for the feed point, and then I will try to do this in a single shot rather than doing iterations as people do. That's wrong. Second thing is that the size of the ground plane, right? It depends on the height, right? So if the size so what I usually do is if I take the length, right, then I'll go length plus say 16 times of the length, so of the height, sorry. And width, let's say, is W, and this is empirical, 16 times of the height plus W. That's going to be the width of the ground plane. So width of the ground plane I'm going to write as WG, which is over here. Okay, and then I'm going to have the length of the ground plane to be LG, which is going to be over here, right? So this is going to be LG. So I have to design five things here: L, W, LG, WG, and then the feed point location. Now, if I take a feed point, right, so the resonance is along the length, right? So these standing wave patterns which you see are along the length. So if the standing wave patterns, as we have seen in case of transmission line also, if there is a discontinuity, there is a standing wave pattern. And now if you want the standing wave pattern, if you have standing wave pattern, then along the length the impedance is going to vary, right? Impedance is infinity at the edges and it is zero somewhere at the center. Now the coupling may change the center, right? So your feed point, which is 50 ohm, is going to change, right? So this is what we know. Now along the width there is no resonance, right? Okay, or we choose W to be much larger than L. What it does is your resonance around W is going to be much lower in frequency. Okay, so resonant along W is going to be much lower in frequency. So your resonant length is L, while W there is no resonance. So in that case the impedance, so if I assume the feed point to be a circle here, so let me draw a feed point. So let's say this is my feed point. Sorry, not good at drawing. Okay, so let's say this is my feed point. So why is it rotating? Okay, so this is my feed point. I choose the feed point to be W by 2. Okay, now if I move this feed point up and down, the impedance is going to change. But if I move the feed point left and right, the impedance is not going to change because W is not the resonant length. Now if I make W comparable to L, which means that instead of this it becomes a square patch like this. So once it becomes a square patch, then the radiation is not only along one of the axis, the radiation is also along the other axis, right? And then the feed point, if it moves on left and right, is going to give you impedance variation also. So this impedance variation I have to establish 50, okay, along the length. So you can see that somewhere between 0 and infinity it is going to be 50. So I have to find that point here, 50. And if it is a square patch, the same distance would be from the other edge also. So somewhere, let's say over here, it will be 50 ohm. So in this case of a square patch, the radiation is going to be X component of E as well as Y component of E, right? Now, if I was to do a slight modification of the patch, right? So how do I do the slight modification of the patch? Let's say I am going to cut this patch over here and here, or if I was to change the relative phase between relative phase of E along one axis and the other axis, if I was to change that relative phase, then I'm going to have a circularly polarized radiation, right? So right now it is a plane polarized, it's along X and Y. Okay, the axial ratio is 1, so basically you have Ex and Ey is going to be 1, and then what you can do is you can cause E to have a certain phase. So as soon as you cause a E on one direction to have a phase difference with E on the other direction, then the Ex plane is going to rotate, and this is going to cause what is called circular polarization, and this can be achieved very easily by cutting the corners. So if you cut the corners, you can introduce a difference in your phase of E, and that will cause the circular polarization. So I told you few things. One is a rectangular patch, the non-resonant length is W, and this will cause no variation of impedance along W. So will be no variation of impedance along W. Next is L is lambda by 2 minus del L. And there this has a standing wave pattern, so it is going to have impedance variation from the center roughly to be 0 to the edge being infinity. Somewhere in between is going to be 50. Either this side or that side, doesn't really matter, right? Either this side or that side, you can choose either of them. If it is a square patch, then it will be somewhere in the corner, equidistant from both the edges, right? So that will cause your Ex as well as Ey. Now if you can introduce some phase difference between Ex and Ey, then you will be able to get the circular polarization or elliptical polarization, right? So a patch can give you any form of radiation. So we are looking at the simplest version. Now let us go ahead and write these equations. I'm going to assume that my dimensions are going to be in microns. So I'm going to go to ADS. Okay, so I have 97 into 3, right? That's the height of the substrate. So I'm going to go here, make a new folder, call this as patch design. Patch design. Okay, let me make sure I'm recording. So it is recording, right? Okay, so let's go ahead and write some equations. Patch design. So I'm going to make a new. Doesn't allow me to do a data set, a data display. Okay, that's a data display. Okay, and I'm going to save it. File, save as, and I'm going to save it as patch patch dash eq equations, patch design equations. Say okay, and this I will put inside the patch design folder, right? So that's the patch design equations. Okay, so I'm going to consider equations. So first is the height. So height is in microns, height in micrometer. That is going to be equal to 97 into 3, correct? So that's the height. So the h in meters is going to be, so h in meters is going to be h in micrometers, h in micrometers, okay, multiplied by 1e6 minus 6. Okay, so this is going to be the height in meters. Now the next input is the frequency. So frequency of design, let's say, is equal to 10 gigahertz. So 10 gigahertz, correct? So that's frequency. Then the next thing is going to be epsilon r, EPSR. Okay, epsilon r is going to be 5.92. Okay. Next is I'm going to write some equation for the non-resonant width. So first of all, I have to compute effective. Yeah, so first of all, I'll write the equation for width in meters. So width of the patch in meters. Okay, so the equation I'm going to write here is 1 divided by 2 pi 2 into frequency into square root of, so this is the square root of mu 0 into epsilon 0, right? So mu 0 goes like this, inbuilt function epsilon 0 goes like this, correct? Right, into square root of epsilon r plus 1, right, into square root of 2 divided by epsilon r plus 1 or in our case it is called EPSR plus 1 bracket close. So square root of that into 1 over 2 twice of frequency, 1 over twice of frequency, square root of mu 0 epsilon 0. Okay, so this is going to be the width in meters, and then the width in microns. So width in micrometer is going to be width in meters, multiplied by 1e6. So this will be width in microns. So let's look at the width. So equations, width in microns. Okay, so it comes out to be 8058 microns. So that is equal to 8.58 mm, right? 8.58 mm. Okay, next is I'm going to write the equation for E effective or epsilon effective. Now the source of E effective is because the fringing is in air, which is 1, and then the dielectric constant is 5.92. So I want to find the equivalent epsilon r for propagation, right? So it's because this is a quasi TEM along the length, so I have to find out uh, E effective, EFF. Okay, E effective is going to be equal to EPSR plus 1, right, divided by 2 plus bracket EPSR minus 1 bracket close divided by 2, right, again bracket close, multiplied by something is going to be 1 divided by SQRT of bracket open 1 plus 10 times of, so this is an empirical equation, H in meters, right, H in meters divided by W in meters, H in meters divided by W in meters, equation close. So this is your E effective, epsilon effective. So let's put that also here. So epsilon effective is going to be lesser than, so it is 5.92 is epsilon r, epsilon effective is 5.569, right? So slightly smaller. Then the next thing I'm going to do is write the equation for lambda. Okay, so I'm going to write the equation for lambda. L, okay, LEMBDA, but I'm going to say LEMDA, or lambda is equal to 1 divided by F into the square root of mu 0 epsilon 0 into E effective, right? Into the square root of mu 0 into epsilon 0 into E effective, bracket close. This is for square root, another bracket close. So this is going to be your lambda in meters. Okay, so this is lambda in meters. Next is I am going to do a length. Okay, so first of all I have to calculate del L, or the reduction in the length which is required due to fringing, del L. So del L is approximately, it depends on the height, right, directly proportional to height. So more the height, more the fringing fields, and larger would be the reduction you have to make, right? So that will be H in meters divided by the square root of uh, E effective. So this will take care of the fringing, right? So now, so L in meters now, right? So next equation would be L in meters. So L in meters would be equal to lambda by 2, lambda divided by 2, lambda by 2 minus twice of del L. So basically fringing is on both the sides, right? So you will subtract del L from both sides. So it will be twice you will subtract. So now H in microns. So L in microns, sorry. L in micrometers. Micrometers will be equal to L in meters into, so L in meters multiplied by 1e6, right? So that will be L in, so let's put there length of the patch. Okay, so the length of the patch comes out to be 6,105. Okay, or 6.1 mm is the length of the patch, right? So now, okay, hang on a second. Okay, so now I'm going to see WG in meters or WG in microns. So let me write the equation here. WG is the ground plane in micrometers would be equal to uh, W in micrometers plus, let's say, 16.4 times of H in micrometer, right? So that is WG. Similarly, L in micrometers, LG will be L in micrometers plus that. So now I have got the ground plane dimensions. So let's put those. So the ground plane dimensions are WG in micrometers and LG in micrometers. So these are your ground plane dimensions. So they are 12 mm, 12.8 mm by 10.8 mm. Okay, so that is the dimension of the ground plane. Now the part comes, which is how do you establish the feed point, right? So in this case, I have to involve the current distribution and the coupling and everything. So this would be involving some kinds of Bessel function for the distribution of current. So let's say I have okay. So I have conductance of the slot. So let's find out the conductance of the slot from the cavity model. So the conductance G1, okay, will be W in meters. Okay, so this is the separation between the radiating slot. So the conductance is going to be large if the spacing between the two radiating slots is increased, right? Okay, divided by some empirical 120 into lambda, right? 120 into lambda multiplied by 1 minus 1 by 6. These are empirical equations, but they will be close to the closed loop, closed physical equations also. Pi times of H in meters divided by lambda square and bracket close. So W meters divided by 120 lambda multiplied by 1 minus 1 by 6 times of, okay, so now the caps has gone. The caps is giving me a problem. So this is going to be pi and this is going to be H meters. Sorry, caps turned on. H underscore meters lambda. Now it will be okay. Okay, sorry about pi into, okay, there is nothing called this. Okay, so now this is the conductance of the radiating slot. Now I have to find out the mutual conductance between the two. So that will be G12. So first of all, I will do because it involves a Bessel function and integral under a Bessel function. So what I have to do is I have to do a theta, okay, over 0 to pi, right? Because 0 to pi is your length L, right? So I have to put here a vector which I'll call theta, right? So theta would be equal to a vector 0 to, and I will do steps of 100, pi by 100, so up to pi, bracket close. So this is my okay. So in ADS you have to put double colons. Okay. So if you see theta, you can plot theta. Doesn't matter. So theta. So what is theta is just a 0 to pi. 0 to pi is theta. So I'm going from 0 to pi, right? And I have 100 samples in between, correct? So that's keep it aside. The next thing I'm going to do is Bessel function of zero order and first kind, which is JA, would be equal to Jn, Bessel function of zero order first kind. So it will be zero order first kind, right? And then I want to do this over sine of theta. So that is my distribution, sine of theta times of L meters, L in meters, times of 2 into pi divided by the lambda. So all I have established here is length in terms of I've established here length in terms of so length in terms of pi, right? So I have done a distribution of sine wave along the length. So that's what this I'm doing a Bessel function of zero order on this dimension, on this vector, right? So that's that. So if I want, I can plot JA, equation JA. So this is going to be that, right? Now next thing I'm going to do is find out the the derivative of that. Okay, so I will call this as G diff. G diff. So this G diff is going to be equal to, so this is the thing which you have to be careful in writing. G diff is for the sine wave into pi into W meters into cos of theta divided by lambda. Everywhere that scaling would be there, divided by cos of theta thing square times of just 1 second. Okay, into something which is sine of theta cube into J. Okay, so that's G diff. So let me plot that G diff. Okay, so that's that. Let's put it on the right hand side axis. Okay, so that's that. Okay, then I will do a G diff versus theta because I want to do an integration, right? So I will combine the two vectors, right? So this will be called G, let's say. So G would be pairing of the two vectors, which we can do versus G diff comma theta. Okay, so now this is along theta now, right? So if I was to plot this G, it will automatically take an angle of, so right now this is versus sample, right? So if I go to this and say plot G, correct, and say add. So now this is along theta from 0 to pi, and this is along the sample, right? So this is G diff, and I need to know the area under this curve, right? So that will give me the mutual conductance, or rather the coupling, conductance due to coupling, right? So So I have to find out the coupling between the two radiating slots. So the conductance due to that would be in parallel with the conductance, which is the self-conductance. So conductance of the radiating slot is this much, and the mutual conductance is G12, which is going to be added along with G1 to give the total conductance of this radiating slot, right? So I will do a ABS of 1 divided by something that is going to be 120 times of my times the square, multiplied with integration under the curve. Integrate. So I'm going to do G, integration of G over the distance pi with the steps pi by 100. So this will give me the numerical integration, isn't it? So let's see what has gone wrong. Absolute value of 1 by 120 pi square into integrate G 0. Oh, one extra bracket I have put. Oh, okay. So this is the mutual conductance. So let's plot here G12. Oh, okay. This is a integration, right? So it will be a single number. So let's delete that. So the integration is a single number, right? So G1. Okay, so G1 is also a number, right? So let me put here G1, conductance of the radiating slot. G1. And then I want to put here G12. So, and I am going to do 5. Okay, so now you can see that the conductance of the radiating slot is this much, and that due to mutual coupling between the two radiating slots is this much. So this portion, the total would be the sum G1 plus G12, right? So now I can establish the feed point has moved, right? So let me establish the feed point. Y in meters, right, will be equal to L meters by pi. L in meters divided by pi. Okay, times of A cos of square root of 2 into Z0. So we didn't put Z0. Okay, so we put Z0. We are designing for 50 ohm, right? Into conductance G1 plus G12, and then bracket close, a bracket close for that one, a bracket close for A cos. So that is why. So Z0 is not there. So let's put here and put Z0. Z0, we are designing for 50 ohm, right? So we want to design an antenna with 50 ohms. Okay, so the 50 ohm point would come around this along the length. So the Y meters is going to be 50 ohm from the edge. So basically, so this is going to be Y meters, because I have done every maths with respect to this L, right? So this L. So this would be Y meters, or I'll put here a small y. Y. So this is your Y. So this is your placement of the feed. Now if you go, the feed goes left and right, there is no variation. But the feed goes up and down, so there is a Z variation. And I have determined where is 50 ohm, okay, on this length L. So you understand how the feed point is computed. Now, most of the designers or the application engineers, they would say, oh, let's put some feed point and let's just move this around. No, that's not how it is designed. You do it by maths. Next is the in case of the incest feed also. Okay, how much do you go in for the incest? Okay, so an application guy will tell you, oh, let's put in something and then we'll put some kind of a tune on this and then look at the response and adjust the 50 ohm. Okay, that's not the way to do it. Okay, you have to know at least rough number on y. You don't search the entire length, right? So this is how you establish the y. So this is how you establish y. So y in microns, y in micrometers is going to be y in meters, y in meters multiplied by 1e6. So that will be y in microns. So let's put here y in microns. So my entire patch antenna design is complete along with the feed point. Not y meters, sorry. Y in microns. Okay, so y in microns is 1361 microns from the edge. From this edge, 1361 microns. So next I'm going to do is I'm going to create this structure of antenna and then put the ports and start simulation. Okay, so I'm going to pause for a second. Okay, so let's go ahead and draw that antenna. So I'm going to start with putting the ground plane. Okay, so I want to put it starting with 0. So the dimensions here are in mm, right? So I'll start this way, tab, and I'll put the dimensions of the ground plane. And the dimensions of the ground plane are uh, 1 point, so it will be 12.830 or 831, 12.831 and 10.878. Okay, 12.831. So let's put here 12.831 mm, and then the next is going to be 10.878, 10.878, 10.878. Okay, so these are the dimensions: 12.831, 12.831 and 10.878. Okay, say okay. So this is your dimension, isn't it? And then I'm going to extrude by the height of it, which is 9 micrometer, and I will call this as a ground plane. Okay, now one more thing is there. In this ground plane I want to put a hole through which I'm going to put the center pin, right? So what is the x and y dimension of that? So wg by 2 would be x dimension, right? So if I take wg by 2, so x dimension would be equal to, so x in mm, okay, would be equal to 12.831 divided by 2, right? And the y dimensions, so y dimension in mm would be equal to whatever is the subtraction of the wg minus w micron, right? So it will be wg micrometer minus w micrometer, okay, divided by 2, okay, divided by 2 plus y, right, plus y in microns. Okay, so this whole thing is in micrometers. Okay, so I will divide by 1000 to show this in mm. Okay, So now I will put here YMM. YMM. XMM is done and YMM. Okay, so this is going to be around 3.747, right? So basically, sorry, I did a mistake. This should be LG and this will be L in micrometers. So is it the same gap? Maybe. Okay, so this is that, and XMM I'm going to put here equations X in mm. So this is where the feed point is. The feed point is at 6.415 and 3.747, right? So I will put here a circle, and the location of the circle would be 6.415. And this will be 3.747. So this number you have to remember, many times you'll use 747. 6.415 and 3.747. So over here is your feed point, and I am going to do a pin. So I have to look at a pin, right? So let's say I do 0.2 mm. So let's say I do 0.2 mm. Okay, so that's that. 0.2 mm. That's too small, isn't it? Let's see if I can increase this. Can't select it. I can do an undo if you want. So let's do this again. Let's put this at 6.415 and 3.747. Correct? And 0.4, 0.5 or 0.5 resistance will be 1 mm thickness, right? Okay, so that's what I will do. 0.5. Say okay. So that's done. So that's the hole in the ground plane. So that's how the ground plane would be, right? That's how the ground plane would be done. Okay, so now on top of it I want to put a substrate. So the substrate will start from 9 micrometer. So that will be the top of the metal, and then it would be starting at 0 and ending at this number, right? And again the height is going to be, so I'm going to make here a pin, isn't it? So I'll use this again, and you know the center is 6.415 and 3.737 or 747. 747, sorry, 747. Say okay. So that's the center of the pin, and I am going to make this as 0.2 radius. 0.2 radius. Okay. So now this is going to be the pin, and then I'm going to go 97 into 3 micron. So what is 97 into 3 micron? So let's look at height. Equations, height in micrometers. 291 microns. 291 microns is the height. right? 291 micron is the height. Okay, 291 micron is the height, correct? And it will look like that, isn't it? And this is going to be substrate, and say done. So that's the metal, sorry, that's the metal, that's the substrate, and the substrate has a hole in it for the pin to go through, right? For the pin to go through, substrate has a hole in it, right? So that's fine. Is it too big a pin? Now maybe the impedance is maybe issue. Let's see later on. 200 micron is 8 mil. 8 mil is not bad. It's fine. Okay. So now I'm going to put here a pin, right? So a pin. So I'm going to make a pin. Again, it would be the center, right? So I'll say tab 6.415 and 3.747. That's the center of the pin. And the pin is 2 micron, right? So the pin is 0.2 mm. Okay. And the height is going to be 291 plus 9. That is going to be 300. So this will come up to the top, 300. And this is called pin, the feed point. And say done. So now that is the pin which is going from the bottom to the top to connect to the patch as a feed point, right? Okay, so now I'm going to do the patch. So to do the patch, I should know X and Y corner. So I will find out XC and YC. So what I'll do is difference divided by 2, isn't it? Difference divided by 2. Okay, so what is the dimension? So let's write that patch dimensions too. I'm going to use L as 8.058 mm, right? So this is going to be width of the patch. 8.058 is the width of the patch, right? So this is in mm. Okay, let me see if I'm recording. Sometimes I forget. How much time? 1 hour. Okay, that's fine. Okay, so that's the width of the patch. And what about the length of the patch? The length of the patch is going to be 6.105. Slightly off, but let's put here 6.105 mm. Correct? So then X and Y locations can be found out like this. So I will say XC in mm would be equal to XC in mm will be W, which is 12.831 minus 8.058, right? This is in mm, divided by 2. So that will be the X location, right? So let's put here X location in mm. So what, 2.3 mm. Is there a problem with this? Why the ground plane is so small? Okay, hang on a second. Okay, so it seems like it's okay. So let's look at YCM, Y corner for Y. YCMM will be equal to uh, the same value, right? It doesn't matter, right? It's going to be same value, 10.878, because we have the 16.4, right, as the extension, right? So it should be the same value, 6.105. So that will be the same value. So YCMM YCMM. Okay, 2.386. So the corner for the patch is 2.386. Okay, so let's go to the patch layout. Okay, so I'm going to create a patch and 9 plus 291 micron, that is 300 micron. 300 micron is the initial height, right? And then I'm going to draw a patch which will start at 2.386. Okay, so it will start at 2.386, 2.386 and 2.386, 2.386. So here it's going to start, and the patch dimensions are given over here. The patch dimensions is 8.058 and 6.105. 8.058, 8.058 and 6.105. 05. That is going to be the patch, and its height is going to be 9 micrometer. 9 micrometers, and I'll call this as patch. Okay, so this is the patch. So now the entire antenna is done. Now I'm going to add the material. So I'm going to add the material from the default material library. So I need silver, and I also need copper. I need copper. I need copper. That's gold, that's copper. So silver and copper are the two things, and then I need a new material definition, and this material is FERRO, ferro tape, right? Ferro A6S, A6S, and this I am going to create as it's not a good conductor. It's a dielectric, right? It's an isotropic physical dielectric. It's a non-dispersive NG mode, loss tangent in this. So its relative permittivity is 5.92, right? And loss tangent is going to be 0.002, right? And appearance, I want to give it a gray color. A gray color. That's okay. And say apply or done. So this is my ferro material, green tape. Now I'm going to assign. So first of all, I'm going to combine, just one second. Okay, so I'm going to combine the pin with the patch. So I choose the first one which I want to keep, and then control the pin, right? And then I can say union, and everything would be a patch. So this is a continuous patch, isn't it? Okay, so I'm going to assign the materials to the patch, and I'm going to keep this as copper. So that's copper. So that's the pin assigned. You can see. So this goes through. This is one material. So this is going to the patch, and then I want to add silver to the ground. So that's the silver to the ground. That's in between layer, right? And then I have ferro going to the substrate. So that's the ferro to the substrate. Now I need to add a port, right? So to add a port, I'm going to go to the bottom view. Okay, and I'm going to zoom in. So I want to create here the port. So first of all, I'm going to add a waveguide port and cancel it out. So I have a port definition here already. So it's a 50 ohm port, right? Voltage source. So next is I'm going to say no definition, and I'm going to choose the first point. The first point is going to be here, and then I'm going to choose the second point. The second point is going to be here. Okay, so first and second point are chosen. then I'm going to say that this is a port which is a 50 ohm port, and I will call this as port 1. Right, so this is a 50 ohm port, and then the extent of the port, you can give some extent, so it's kind of horrible, so I'm not going to give an extent to the port. I'm going to just make sure that this is connected. So this is not connected, so I will choose, sorry, not the extent, I'll choose this to be here, isn't it? What happened? View all. Oh my god, cancel it. Wow. Okay, what happened to my antenna? Is there an undo? Oh, this has to do with the graphics. Save project, call this as rect match. Something messed up. Okay, I'm going to go here and open this again. Okay, okay, close bottom view. Okay, do we have no material assignment? Okay, okay, I think sub is not assigned, right? So sub is assigned. Okay, so now this is okay. Right, so let's go to the bottom, and I'm going to put here the port. Is there a port definition here? Right, insert port, no definition. Come on. That's there. Let's zoom in further. Zoom out. That's the maximum extent I can zoom in. Right, so this is connected. And let's look at the other side. That's that. So if I zoom in, that's connected to. So this is port 1, and this is a 50 ohm port, and say done. Okay, so this is my definition of the port, and I look at the top view and say view all. So now I'm ready for the simulations, right? So I'm going to say save project, and then set up for simulation, and I'm going to go from 9 gigahertz, so it is designed at 10 gigahertz, right? 9 gigahertz to 11 gigahertz. 11 gigahertz is too big a distance, isn't it? Too big a range. 9 gigahertz to 11 gigahertz. Max point is, let's say, 50. Okay, so this is adaptive. Mesh refinement after advanced use the best conversion, correct? And then solver is direct, and then everything is fine, and then I can say create in queue simulation. So let me see if I'm recording. Yes, I am. So the simulations have started. So this is your adaptive meshing, and the idea is the error has to go below 0.01. Okay, so the meshing is done. Now it will simulate the frequencies. So okay, so this is done. Let's look at the results. I want to look at S11. So here I am going to look at S11. So let's see a marker. So 10 gigahertz, 10 gigahertz. Okay, 9.7. Okay, which is way out there. So it seems like we might have to adjust this to get the 10 gigahertz at the center. So this is a 11 gigahertz point and this is a 9 gigahertz point, and this antenna is at 9.7. So if I was to do a rectangular plot of this, so you see that this is not tuned here. This has to be tuned at 10, right? So I'm going to adjust this, but meanwhile I'm going to put you on pause. Once I have a final adjustment, I'll there will be slight movement of the feed point. So I'll inform you. Okay, thanks. Okay, so now what I have done is I have slightly moved the feed point. So let's look at the geometry. Okay, so I have moved the feed point up by 0.5 mm, right? And I have shrunk the length by 0.22 mm, so 0.11 mm on each side. So I shrunk the length by 0.11 mm, and I moved the feed point up, and I took 8 iterations to do that to arrive at the result. So I arrived at this result, which is in Smith chart is like that, and in XY plot it's going to be like this. So I have done that. Now I want to look at the patterns. So what I'll do is I have to do one more simulation for including the sensors. So I want to have a far zone sensor here, and I am going to go up to theta 5. So I am going to go 360 on. So I want to look at the back lobes also, increment of 5 degrees, and say apply. So now I have this antenna which is in this computation space, and I'm going to look at the far field, what its pattern going to be. So I have to just say done. So that's the antenna I have, right? So that's the antenna I have, and I'm going to say create in queue simulation. Okay, so this is my 9th simulation to look at the far field. Okay, let me see if I'm recording it. Yes, I am recording it. I don't want to exceed 1 hour 25 minutes. So let's this fix the mesh. Error is delta S is 0.019. 2 more iteration probably. Yeah, 1 more iteration done. So now we are going to compute your S parameters, your fields, and then compute S parameters. So that's what it is doing right now. It is adaptive, right? So the closest point I have is 10.33 where I designed, right? So I'm going to plot everything at 10.33. Okay, so now it is computing the far field pattern, and it is done. So let's look at the results. Okay, so the 9th one, you can look at S parameters. Nothing stops you looking at S parameters. They are the same, right? So I'm sitting at 10 point. Oh, so what is this frequency point? So this is 10 gigahertz. Should have a 10 gigahertz point in there, right? So now I want to look at the net power, radiation efficiency, realized gain. I think I should be looking at the realized gain, isn't it? So okay, so that's what the antenna normalized pattern looks like. This is at, I want to do this at 10 gigahertz, right? And single excitation line graph, and so I'm going to look at the total display. Just 1 second. Pattern not selected. Okay, so okay, for me also some things have changed in this software, but first of all I want to see what happened to the gain pattern. So I can always go to gain and I can plot that pattern. So basically that's the gain pattern here in 3D. Now let me pause this, let me close this. So I don't want to see this one, right? Okay, so we are looking at here the far field pattern from the far field sensor at 10 gigahertz. And if you want to display the pattern, uh, you can choose from where? Single excitation line graph, right? So in the line graph you can choose what you want to plot. Okay, so let's say I'm plotting here the gain, right? So this is the gain. So I'm looking at 10 gigahertz frequency. I'm looking at independent axis theta for a given phi equal to 0, and I can make a new graph. Okay, so say view. So this is going to be my versus theta, my pattern. And in this case I can look at the gain of this antenna is 4.83 at this frequency, 4.84 dBi. That's the gain, and the back lobe is minus 3.23 dBi. So front to back lobe ratio is going to be 4 and 3, 8. Roughly 8 dB is the front to back lobe ratio. Now this is because the ground plane is very small. So you can work with the ground plane. You can increase the size of the ground plane and then reduce this back lobe ratio, right? So this is something which you can do over a period of time. So that's not what I wanted to show you. Now this is gain. Now let's look at radiation efficiency, right? So let's go to radiation efficiency, right? And here, okay, it's giving you a table. If you want, you can plot them too. So what I'm looking at is at 10 gigahertz, the radiation efficiency is 79.460%, and the system efficiency is this 76.69. Okay, and so you can see across the frequency from 9 to 11 gigahertz, the radiation efficiency goes from 63.3 to 70.3, peaking at 79 at 10 gigahertz. And system efficiency is basically the return loss, right, into the picture also. So from 9.6 gigahertz to 10.16 gigahertz, 10.3 gigahertz, this looks like okay, up to 26 or 25% efficiency, system efficiency. Now that means that this antenna is very narrowband. So from your S parameters also you can see that this antenna is a very narrowband antenna. So have a look at it. So this is a very narrow band antenna. So that's the basic problem of the patch antennas, is that they are very narrow band. So now there are ways to make it broadband. So to make them broadband, there are two ways of doing that. One is basically the shape of the antennas. The other is the slots which you can cut in the ground plane or in the patch, right? That's another way. And the third way is you can introduce distorted ground, right? So basically you can introduce what you call electromagnetic band gap or EBG structures in between the ground and the patch, and that way you can make this a broadband antenna. So that's not the part of this session, so I'm going to leave it there. Now one more thing I can visualize, okay, from here. Okay, so one more thing I can visualize is if I look at the surface sensors. So if I'm going to look at the surface sensors. Okay, so here what I want to see is at 10 gigahertz, I want to plot uh, uh, let's say this on copper, and so I will have to, okay, so just a second, auto repeat, and I have to plot this flat. So I'm going to plot first the current densities, right? So let's get rid of this guy. Okay, so I don't want this field, I want the geometry, right? So is that the one? Yeah. Now is that gonna work here? Copper. Okay, I want to look at this. Where is the enable for this? So let me go to results and let me go to this. This is what we are trying to do, right? Now I don't want to see the pattern. I just want to see the currents. So unload this, is it? Unload. Okay. So this is the antenna. Yeah, and there's the pattern. Okay. So now they have slightly changed GUI. So I'm plotting the currents on this patch, and what I want to do is I want to look at the fine, and now fine is too much, is it? Normal. Okay, let's go normal only, and I want to repeat it, and also I want to change this legend. Instead of auto range, I'm going to go to properties and put this current to something like 20, isn't it? And say done, and hit play. So what I'm playing is basically this is my input, which is going 0 to 360, and you can see the currents. Look at the edges, right? Let's go down further to 10. Okay, so now you can see what current waveforms I was talking about. So there is a standing wave pattern here you can see of currents, right? And across the patch you can see that, right? If you put it under fine, so let's put pause and put it under fine, probably you will get more clear visualization. Okay, so you can see the currents are going to reverse the directions, right? So they have the maximum at the center, right? So that's what I basically plotted here, right? So this is what the current is doing. This is what the current is doing. Over here, this is what the current is doing. And the feed point is over here, right? So that's all you can visualize here, right? So I think I'm gonna end the video here. The visualization in ADS is much better than in EMPro. So I'm gonna stop here. Thanks a lot. Thank you.